Hello and welcome to the stream. This is day 8 of learning OpenGL. We have completed the getting started section. So now we're going to be moving on to the lighting section, beginning with the colors. All right, let's get into it. We briefly used and manipulated colors in the previous chapters, but never defined them properly. Here we'll discuss what colors are and start building the scene for the upcoming lighting chapters. In the real world, colors can take any known color value, with each object having its own colors. In the digital world, we need to map the infinite real colors to a limited digital values, and therefore not all real world colors can be represented digitally. Colors are digitally represented using red, green, and blue components, commonly abbreviated as RGB, using different combinations of just those three values within a range of 0 and 1. Okay, this is fairly basic stuff. So in OpenGL, we use GLM Vec3 data structure. And here you can see he has defined a coral color. This will be the red, the green, and the blue channel for that color. All right. And then here is like a basic model of how lighting works. You have your main light source. This is white light, and if it hits an orange surface, it absorbs all the lights except for the and reflects the light that we see, that part of the light that we see. And here it's like reflecting the orange color, so we see this object as orange. That's fairly simple. Technically it's a bit more complicated, but we'll get into that in the PBR chapters. These rules of color reflection apply directly in graphics land. When we define a light source in OpenGL, we want to give this light source a color. In the previous paragraph, we have a white color, so we'll give the light source a white color as well. If we would then multiply the light color with an object's color value, the resulting color would be the reflected color of the object, and thus its perceived color. Okay. So since if a light source is tinted, like if it's not a purely white light, then that will have an effect on what the perceived color of the object is. So how do we do that in the so-called graphics line? What we do is we just multiply the light's color value with the object's color value. So here is the example. The light is going to be 111, which means just white light, and then the toy is 1.5 and 0.3, which will be maybe reddish, orangish, something. And then to get the resulting color of that object, you just multiply the two lights, and then here you can see, because this is just white light, it will be exactly equal to whatever the color of the object is. Okay, as we can see, the toy has no red and blue light absorb and reflect. The toy also absorbs half of the light's green value, so also reflects half of the light's green value. Here it doesn't have, the light has no red color in it, so that's why when this gets multiplied by the red color of the object, it just becomes 0, so we're not going to see the red of the object. Here the light color has a value of 1. That means however much green it has, that will show through exactly. And then it has no blue. That means this is just a green light. It has no red or blue component. That means the blue component of the object color will also be just 0, and then we'll only see the green color. That's why when you're in like a blue light or green under green light, everything looks that color, but it's just different shades of green. Okay, let's try one more example with the dark olive green. So this is green color, but it does have other components as well. So these will act like scaling values for these colors. And here you can see when we multiply these two, colors get changed based on the color of the light. As you can see, we can get interesting colors from objects using different light colors. It's not hard to get creative with colors, but enough about colors. Let's start building a scene where we can experiment in. Okay, I actually forgot to open the project. Let me just do that real quick. In the upcoming chapters, we'll be creating interesting visuals by simulating real-world lighting, making extensive use of colors. Since now we'll be using light sources, we want to display them as visual objects in the scene and add at least one object to simulate the light from. The first thing, excuse me. All right, I'm back. The first thing we need is an object to cast a light on, and we'll use the infamous container cube from the previous chapters. We'll also be needing a light object to show where the light source is located in the 3D scene. For simplicity's sake, we'll represent the light source with a cube as well. We already have the vertex data, right? So filling a vertex buffer object, setting vertex attribute pointers, and all that jazz should be familiar for you by now. So we won't walk you through those steps. If you have no idea what's going on, then I suggest you review the previous chapters and work through the exercise if possible before continuing. So the first thing we'll need is a vertex shader to draw the container. The vertex positions of the container remain the same, although we won't be needing texture coordinates this time. So the code should be nothing new. We'll be using a stripped down version of the vertex shader from the last chapters. Okay, we have our MVP here and then the position of the vertices. Make sure to update the vertex data and attribute pointers to make the new vertex shader. If you want, you can actually keep the texture data and attribute pointers active. We're just not using them right now. Because we're also going to render a light source cube, we want to generate a new VAO specifically for the light source. We could render the light source with the same VAO and do a few light position transformations in the model matrix. But in the upcoming chapters, we'll be changing the vertex data and attribute pointers of the container object quite often, and we don't want these changes to propagate to the light source object. We only care about the light cube's vertex positions, so we'll create a new VAO. Okay, so it's creating a new VAO for the light. We need to bind to the VAO containers VBO already contains, right? Okay, the code should be relatively straightforward. Now that we created both the container and the light source cube, there is one thing left to define, and that is the fragment shader for both the container and the light source. Okay, so the fragment shader the same? The fragment shader accepts both an object color and a light color from a uniform variable. Okay, the light color and the object color. Here we multiply the light's color with the object's reflected color like we discussed at the beginning of the chapter. Again, this should be easy to understand. Let's set the object's color to the last section's coral color with a white light. One last thing to note is that when we start to update these lighting shaders in the next chapters, the light source cube would also be affected, and this is not what we want. We don't want the light source object's color to be affected in the lighting calculations, but rather keep the light source isolated from the rest. We want the light source to have a constant bright color unaffected by other colors changes. This makes it look like the light source cube really is the source of the light. To accomplish this, we need to create a second set of shaders that we'll use to draw the light source cube, thus being safe from any changes to the lighting shaders. The vertex shader is the same as lighting vertex shader, so you could simply copy the source code over the fragment shader of the light source cube and shows the cube's color remains bright by defining a constant color value on the lamp. Yeah, so we need a different fragment shader for the light as well. When we want to render the container object or possibly many other objects using the lighting shader we just defined. And when we want to draw the light source, we use the light source's shaders. During the lighting chapters, we'll gradually be updating the lighting shaders to slowly achieve more realistic results. The main purpose of the light source cube is to show where the light comes from. We usually define a light source's position somewhere in the scene, but this is simply a position with no visual meaning. To show where the light source actually is, we render a cube at the same location of the light source. We render this cube with the light source cube shader to make sure the cube always stays white regardless of the light conditions of the scene. So let's declare a global vec3 variable that represents the light source location in the world space coordinates. Then we're gonna translate it there, light pos in the model matrix code. The resulting render code for the light source cube should then look something like this. Injecting all the code fragments at the appropriate locations. Okay, so this is the right light source and this is the object. Not really much to look at, but I'll promise we'll get more. Okay, let's just set this up real quick. Yep, others are the same. Let's see where we are. Okay, yeah. We have multiple objects. We don't need that many objects. Or we could keep them. Okay. So first things first, what he's done is created a vertex shader. This takes the MVP. Let's take a look at our vertex shader. Okay, where is this? Okay. So we don't need the texture coordinates. It's location 1. Let's get rid of that. Why do I have domains? Okay. So all of this texture stuff is useless. We don't need this. We don't need this texture either. Maybe I should just keep a copy of this. That's fine. Okay, let's take the image. One, two, three, four, five. I think this is the vertex location and this is the texture coordinates. So we got rid of the texture coordinates. Okay, I might need new vertices. Okay, we have our MVP. Texture coordinate. Don't need that. Okay, yeah, they're white color now. This is the wait, what is this for? Okay, yeah, this is the texture coordinate. It's fine, we can just leave it there. Okay, what else do we need? This is our vertex shader right here. So EVM vec4 with a position. Yep, it's exactly like this. And then make sure to update the vertex data because we're also rendering a light cube. We want to generate a new VAO. So let's make a new VAO. per our object. Let's create the light here. Okay, it'll be exactly like this. GL gen vertex arrays. Then GL bind vertex array. You only need to bind to the VBO. The container's VBO data already contains the data. Okay, so in that case, we should do it after the object. GL bind buffer, GL array buffer, VBO. So the vertex attribute. Okay. So then, so we have a shader here. The code should be relatively straightforward. Now we create both container and the light source view. Light view. We copy into this. So this is the frag color. We have our frag color like usual, and we need two uniforms: object color and light color. And then we need to multiply them. Cool. The fragment shader accepts both an object color and a light color from the uniform. Here we multiply the light's color with the object's reflected color like we discussed at the beginning of the chapter. Again, this shader should be easy to understand. Don't forget to use the corresponding shader program first to set the uniform. Okay, we have to create a light shader. So this is our shader. Let's create the light shader. Where is it? Okay. And then we set the object color and the light color, which is right here. One thing I have to notice that we start to update the lighting shaders in the next chapter. The light source cube would also be affected, and this is not what we want. So this is for the light source. Lighting shader, and then this will be, wait a sec. This is like a lit shader to be lit by the light. And then let's create, oops, an unlit shader. This is set all for vertex values to 1. This is just gonna be constant for color. Okay. server unlit. Do we need this? Okay, we need a set to vec3. Do we have a source code somewhere? Okay, quite progress. When we want to render the container object or possibly many other objects using the lighting shader. Okay, yeah, we did that, and we just defined. And when we want to draw the light source, we use the light sources shader. During the lighting chapters, we'll gradually be updating the lighting shader, so slowly achieving more realistic results. The main purpose of the light source cube is to show where it is. Okay, so we need to set a GLM vec3 for the light position. I guess we can set it anywhere, but let's just set it at the top here. When we translate the light source cube to the light source's position and scale it down before rendering, so okay, this is using the light position. The resulting render code for the lighting source should look like something like this. Just need data for a single cube actually. Okay, these are just the positions. So this is gonna change. First, you configure the cube's VAO and VPO. Right here. Don't need the texture coordinates anymore. It's only 3 now. And then configure the lights. VAO and VPO stays the same. The vertices are the same for the light object, which is also a 3D cube. Okay, he's doing the shader stuff inside. I went over, of course. We'll move it later. So that's our cube object. And for the lighting, it's doing the same thing. We got the lighting VAO. We're generating the buffer, binding the buffer. Jails and bind the VBO. Setting the attribute here. Okay. Got the input, clear color and everything. Okay. Then it's using the lighting shader here. Then the MVP for the object. I'm doing GL vertex array for some reason. Let's get rid of that. Okay, we got our model. Okay, it's doing model last. Okay, projection, perspective, radians, camera zoom, it's the same. Lighting shader. Okay, I have the projection and the view. The model was supposed to be in this, but now I'm not doing multiple objects anymore. So I can just do that here. Cool. Okay, rendering the cube. For that, we bind the cube's VAO, which is just called VAO in my case, and then GeoDraw arrays. I'm still not using elements. Dude, what? Okay, he's doing the static cast float. So I already have a model. Then I'm rotating it. So I'm gonna just do it like this. Okay, so what is this? Just rotating the model for some reason. I'm kind of curious what this is. Not even setting it there. Yep, that also will. Is it rotating? If I'm creating it again and setting it to this, then I rotate, is it? Yep, there we go. Okay, back to the problem at hand. That works. Let's draw the light. So for that, we're going to use the light shader, set up our MP, and then set the VAO, then OpenGL draw arrays. Okay. Light cube shader. You just change names. Okay, so the light cube shader will just be a normal unlit shader. I think I just call it unlit shader. Light cube VAO. What am I calling that? Light VAO. Yep, there's our light source. Okay. The view and the projection is fine, but for the model, we're first translating it to where the light position is, and then it's scaling it to create a smaller cube. Alright, so I guess that's it for the setup for the lighting chapters. Surprisingly. Alright, let's crack on. So for the basic lighting in the real world is extremely complicated and depends on way too many factors, something we can't afford to calculate on the limited processing power we have. Lighting in OpenGL is therefore based on approximations of reality using simplified models that are much easier to process and look relatively similar. These lighting models are based on the physics of light as we understand it. One of these models are called the Phong lighting model. The major building blocks of the Phong lighting model consist of three components: ambient, diffuse, and specular lighting. Below you can see what these lighting components look like. Okay, so this is probably the final result that we're looking for. Ambient is like the even lighting. Even when it is dark, it's usually lit by something somewhere in the world, the moon, the distant light, whatever. And then the diffuse lighting is the directional impact a light object has on an object. And then the specular is the bright spot that appears on shiny objects. Cool. I guess ambient lighting will be the easiest. Light usually does not come from a single light source, but from many light sources scattered all around us, even when they're not immediately visible. One of the properties of light is that it can scatter and bounces in many directions, reaching spots that aren't directly visible. Light can thus reflect on other surfaces and have an indirect impact on the lighting of an object. The algorithms that take this into consideration are called global illumination algorithms, but these are complicated and expensive to calculate. Since we're not big fans of complicated and expensive algorithms, we'll start by using a very simplistic model of global illumination, namely ambient lighting. As you've seen in the previous section, we use a small constant light source that we add to the final resulting light of the object's fragments, thus making it look like there is always some scattered light even when there is no direct light source. Adding ambient lighting to the scene is really easy. We take the light's color, multiply it with a small constant ambient factor, multiplying this with the object's color, and use that as the fragment's color in the cube object shader. Okay, so we have something called the ambient light and the ambient strength. We multiply that by the light color. So there's like a very faint color even if there is no light. Okay, this should be easy. Let's try that on the fragment shader. Then we just multiply ambient with the color of the object. Cool. Okay, so now this is the ambient color of the object. Even in shadows, that will be the color that we see. If you now run the program, you'll notice that the first stage of lighting is now successfully applied to the object. The object is quite dark, but not completely, since ambient lighting is applied. Note that the light cube is unaffected because we use a different shader. It looks something like this. Yeah. Diffuse lighting. Ambient lighting by itself doesn't produce the most interesting results, but diffuse lighting, however, will start to give a significant visual impact on the object. Diffuse lighting gives the object more brightness. The closer its fragments are aligned to the light rays from a light source. To give you a better understanding of diffuse color, take a look at the following image. Okay, so we actually need to calculate the angle between the light ray and the surface normal, and the less the angle is, the brighter that fragment will be. To the left, we find a light source with a light ray targeted at a single fragment of our object. We need to measure at what angle the light ray touches the fragment. If the light ray is perpendicular to the object's surface, the light has the greatest impact. To measure the angle between the light ray and the fragment, we use something called a normal vector. That is a vector perpendicular to the fragment's surface, here depicted as a yellow arrow. We'll get to that later. The angle between the two vectors can then easily be calculated with the dot product. Okay, yep, this is just same thing. So what we need to do, calculate diffuse lighting, normal vector, a vector that is perpendicular to the vertex's surface. The directed light ray, a light direction that is the difference vector between the light's position and the fragment's position. To calculate this light ray, we need the light's position vector and the fragment's position vector. A normal vector is a unlit vector that is perpendicular to the surface of a vertex. Since a vertex by itself has no surface, it's just a single point in space, we retrieve a normal vector by using its surrounding vertices to figure out the surface of the vertex. We can use a little trick to calculate the normal vectors for all the cube's vertices by using the cross product. But since a 3D cube is not a completed shape, we can simply manually add them. Oh, it's not a complicated shape. We can simply manually add them to the vertex data. The updated vertex data array can be found here. Try to visualize that the normals are indeed vectors perpendicular to Each plane surface AQ consists of 6 planes. Okay, so now these first three are positions, and then these are the normals for those vertices. Okay. So we need to add that here. Yeah, we're not using this anymore. Okay, that means we need to update our GL trip pointers. It's now 6, 1, 2, 3, 4, 5, 6. Yep. And we probably need to add another one for the size. Now that we added a normal vector to each of the vertices, they updated the vertex shader. We should update the vertex attribute pointer as well. Note that the light sources cube uses the same vertex array for its vertex data, but the lamp shader has no use of the newly added vertex vectors. We don't have to update the lamp shaders or attributes configuration, but we have to at least modify the vertex attribute pointer to reflect the new vertex array's size. That is true. Here we need to add this. Okay. Think this will be the size of times 3 stride. I'm not sure I remember. When you want to use the first 3 floats of each vertex and ignore the last 3 floats, so we only need to update the stride. That's for the light bit. What about the cube? The normal attribute. Okay, this needs to be 1. 6 times size of float. Okay, yeah, 3 times size of float. So yeah, this was correct actually. I just need to put parentheses. I guess it's better to say what these attributes are. Okay, where were we? All the lighting calculations are done in the fragment shader, so we need to forward the normal vectors from the vertex shader to the fragment shader. Let's do that. So we're just gonna have an out normal vector, and then it's just gonna pass it on. Okay, what's left to do is declare the corresponding input variable in the fragment shader. So that will be our inside our fragment shader. Calculating the diffuse color. We now have the normal vector for each vertex, but we still need the light's position vector and the fragment's position vector. Since the light's position is a single static variable, we can declare it as a uniform in the fragment shader. Sure. And then update the uniform in the render loop or outside it since it doesn't change. Lighting shader to set vec3. Yep. Let's do it here. This is the unlit shader. Then the last thing we need is the actual fragment's position. We're going to do all the lighting calculations in world space, so we want a vertex position that is in world space first. We can accomplish this by multiplying the vertex position attribute with the model matrix only, not the view and the projection matrix, to transform it to world space coordinates. This can easily be accomplished in the vertex shader, so let's declare an output variable and calculate its world space coordinates. Okay, so in the vertex shader, we're going to have an out frag position, and then this will be the frag position. It will just be the position of the vertex multiplied by the model matrix. That will give us the world space position of that fragment. Okay, got it. And lastly, add the corresponding input variable in the fragment shader. Yeah. The invariable will be interpolated from the three world position vectors of the triangle to form the frag boss vector that is the per fragment world position. Now that all the required variables are set, we can start the lighting calculations. The first thing we need to calculate is the direction vector between the light. Wait a second. I'm just gonna run without doing anything. Yeah, okay, so we're still don't have any errors. The first thing we need to calculate is the direction vector between the light source and the fragment's position. From the previous section, we know that the light's direction vector is the difference vector between the light's position vector and the fragment's position vector. As you may remember from the transformations chapter, we can easily calculate this difference by subtracting both vectors from each other. We also want to make sure all the relevant vectors end up as unlit vectors, so we normalize both the normal and the resulting direction vector. All right. We have the norm and the lighting direction. So this is gonna be inside main. So after we calculate ambient, we're gonna calculate our normal, which will just be the normalize normal, and our light direction, which will be the normalized form of the light position minus frag position. Yep. So that's our direction of the light and the normal. Then we just gonna dot product. Yep. When calculating lighting, we usually do not care about the magnitude of a vector or their position. We only care about their direction. Because we only care about their direction, almost all the calculations are done with unit vectors, since this simplifies most calculations. All right, so always make sure you normalize your vectors. Next, we need to calculate the diffuse impact of the light on the current fragment by taking the dot product between the norm and the light direction vectors. The resulting value is then multiplied with the light's color to get the diffuse component, resulting in a dark diffuse component the greater the angle between the two vectors. So we're taking a dot product, and if it gives a negative value, let's just set that to 0. That will be our diffuse. And finally, diffuse is equal to diffuse times light color, which in this case is just, why don't we just do it like this? Light color, diffuse. And then we're just gonna, okay, we're gonna add them. If the angle between both vectors is greater than 90, then the result of the dot product will actually become negative, and we end up with a negative diffuse component. For that reason, we use the max function. Now that we have both an ambient and a diffuse component, we add both colors to each other and then multiply the result with the color of the object to get the resulting fragment output. So that will be our frag color. That actually looks like a cube now. If your application in shader compiles successfully, you should see something like this. You can see that with diffuse lighting, the cube starts to look like an actual cube again. Try visualizing the normal vectors in your head and move the camera around the cube so to see that the larger the angle between the normal vector and the light's direction vector, the darker the fragment becomes. In the previous section, we passed the normal vector directly to the vector shader from the vector shader to the fragment shader. However, the calculations in the fragment shader are all done in world space, so shouldn't we transform the normal vectors to world space coordinates as well? Basically, yes, but it's not as simple as simply multiplying it with the model matrix. First of all, normal vectors are only direction vectors and do not represent a specific position in space. Second, the normal vectors do not have a homogeneous coordinate, the W component of a vertex position. This means that translations should not have any effect on the normal vectors. So if we want to multiply the normal vector with a model matrix, we want to remove the translation part of the matrix by taking the upper left 3 by 3 matrix of the model matrix. Note that we could also set the W component of a normal vector to 0 and multiply with the 4 by 4 matrix. Second, if the model matrix would perform a non-uniform scale, the vertices would be changed in such a way that the normal vector is not perpendicular to the surface anymore. The following image shows the effect such a model matrix with non-uniform scaling has on a normal vector. Okay, so in that case, it wouldn't be perpendicular to the surface anymore. Whenever we apply a non-uniform scale, not a uniform scale only changes the normal's magnitude, not its direction, which is easily fixed by normalizing it. The normal vectors are not perpendicular to the corresponding surface anymore, which distorts the lighting. The trick of fixing this behavior is to use different model matrix specifically tailored for normal vectors. This matrix is called the normal matrix and uses a few linear algebraic operations to remove the effect of wrongly scaling the normal vectors. If you want to know more about, look at this article. The normal matrix is defined as the transpose of the inverse of the upper left 3 by 3 part of the model matrix. That's a mouthful, and if you don't really understand what that means, do not worry. We haven't discussed inverse and transpose matrices yet. Note that most resources define the normal matrix as derived from the model view matrix. But since we're working in world space and not in view space, we will derive it from the model matrix. In the model matrix, in the vertex shader, we can generate the normal matrix by using the inverse and transpose functions in the vertex shader that we work on any matrix type. Note that we can cast the matrix to a 3 by 3 matrix to ensure it loses its translation properties and that it can multiply with the vector 3 normal vector. Okay, taking the model matrix, inverting it, transposing it, it will give us a 3 by 3 matrix, and then multiplying that by the normal. Inversing matrices is a costly operation for shaders, so whenever possible try to avoid doing inverse operations since they have to be done on each vertex of our scene. For learning purposes that is fine, but for an efficient application we're likely going to calculate the normal matrix on the CPU and send it to the shaders via a uniform before drawing, just like the model matrix. Okay, since we're not doing any scaling, that's why we don't need to do all of this stuff. If you're doing it non-uniform scale, however, it is essential that you multiply your normal vectors with the normal matrix. Okay, finally the specular lighting. If you're not exhausted already by all the lighting talk, we can start finishing the Phong lighting model by adding specular highlights. Similar to diffuse lighting, specular lighting is based on the light's direction vector and the object's normal vectors, but this time it is also based on the view direction. For example, from the direction the player is looking at the fragment, specular lighting is based on the reflective properties of surfaces. If we think of the object surface as a mirror, the specular lighting is the strongest wherever we would see the light reflected on the surface, and we can see this effect in the following image. Okay, so it's kind of similar to diffuse. We have the normal and the reflected ray, and then we want to calculate the angle between the reflected ray and the angle that we're looking at it. We calculate the reflection vector by reflecting the light direction around the normal vector. Okay. We calculate the angular distance between this reflection vector and the view direction. The closer the angle between them, the greater the impact of the specular light. The resulting effect is that we see a bit of a highlight when we're looking at the light's direction reflected via the surface. The view vector is the one extra variable we need to for specular lighting, which we can calculate using the viewer's world space position and the fragment's position. Then we calculate the specular's intensity, multiply this with light's color, and add this to the ambient and diffuse components. We choose to do the lighting calculations in world space, but most people tend to prefer doing lighting in view space. An advantage of view space is that the viewer's position is always at 0, 0, 0, so we already got the position of the viewer for free. However, I find calculating lighting in world space more intuitive for learning purposes. If you still want to calculate lighting in view space, you want to transform all the relevant vectors with the view matrix as well. Don't forget to change the normal matrix too. To get the world space coordinates of the viewer, we simply take the position vector of the camera object, which is the viewer, of course. So let's add another uniform to the fragment shader and pass the camera position vector to the shader. Okay, so now the shader needs to know where the viewer is. We can pass that as a uniform. Lighting shader. Still not going to do that. Now that we have all the required variables, we can calculate the specular intensity. First, we define a specular intensity value to give the specular highlight a medium bright color so that it doesn't have too much of an impact. This will be here though. Okay, we shouldn't put this in the vertex shader. We can just directly have it in the fragment shader. If we would set this to 1, we'd get a really bright specular component, which is too bright for the coral cube. In the next chapter, we'll talk about properly setting all these lighting intensities and how they affect the object. Next, we calculate the view direction vector and the corresponding reflect vector along the normal axis. So view direction is just going to be the viewer's position and the position of the fragment. Subtract that and we normalize it. That is the view direction. And the reflected is, okay, there's a reflect function. You give the light direction negative sign and you tell it which vector to reflect, I guess. Note we negate the light direction vector. The reflect function expects the first vector of point from the light source towards the fragment's position, but the light direction vector is currently pointing other way around. Yeah, okay, so it's going like this. We want to be like that. From the fragment towards the light source, this depends on the order of subtraction earlier in which we calculated the light direction vector. Okay, so we have both of those. Then what's left to do is actually calculate this. So we do a dot product similar to diffuse, and then we take the maximum so it doesn't go negative, but then it's doing a power of 32. This is accomplished with the following formula. We first calculate the dot product, make sure it's not negative, and then raise it to the power of 32. This 32 value is the shininess value of the highlight. The higher the shininess value of an object, the more it properly reflects the light instead of scattering all around, and thus the smaller the highlight becomes. Below you can see the image that shows the visual impact of different shininess values. Okay, so that's how you get your specular reflection. And all you have to do is your specular strength multiplied by the spec that you calculated and the light color, of course. That'll give you your specular part of the light, and then I guess we just add it. Yep. Plus specula. Let's go, let's go, let's go. Damn, it's kind of dark. Okay. I mean, it's kind of hard to tell. Should I rotate the cube? I think that would be interesting. Yeah. This matrix, rotate, matrix again, and then the angle should just be 1 degrees, and then geometry. Let's rotate it on the Y. See, that is not good. There must be a better way to do this. Can we just multiply it by the time? Not sure I'm seeing any specular highlight here. Let's try removing it. Maybe that'll be able to see the difference. Yeah, I guess I kind of see the difference. This looks rough, and then with this specular, it does look a bit shiny, does it? Is it just me? Okay, let's make it more shiny then. Let's use 256. Okay, and now we clearly see the effect. Okay, where is it? Okay, there we go. It's kind of cool. Yep. Okay, I guess that's it. You can find the complete source code here, and then it's talking about types of shading. Okay, developers use to implement Phong lighting model in the vertex shader. The advantage of doing lighting in the vertex shader is that a lot more efficient since you're generally a lot less vertices compared to fragments. But it has this kind of visual artifacts. Yeah, it looks it's interpolated. The result was that lighting was not very realistic unless large amount of vertices were used. When Phong lighting model is implemented in the vertex shader, it's called Grodd shading instead of Phong shading. Note that due to the interpolation of lighting looks somewhat off, the Phong shading gives much smoother lighting results. Okay, I guess that's it. Stream has been going on for almost 1 hour, 20 minutes. Okay, we have a comment. I want to offer a promotion to your channel before chat. Don't know about that. Alright, that's it for today's stream. If you want to follow along, you can actually inside of Twitch, twitch.tv/codestrum. You will actually see the link to the YouTube channel right here. Go to the YouTube channel and you'll find all of the previous videos. There's even the playlist, so I will also upload this as day 8 over here, and that way you can follow along from the beginning. Next week we're going to be doing materials, which is going to be awesome. Cool. Yep, that's it for tonight. See you guys next week. Bye.